Hello everyone, this is Jim Chastain with EasyPower. Welcome to the EasyPower webinar series. Before I introduce our guest speaker for today on a very informative presentation, I'd like to run a couple poll questions and get some feedback from the audience to help kind of focus our discussion. So the first question is, what best describes your market? If you would please assist us by providing some feedback. We expect to be fairly highly attended today based upon the registration for this webinar. So we're glad to hear that there's so many people with interest in this particular topic. So it looks like we have a quorum on this first question. Here's how people have weighed in on this. Good. The second question is, what best describes your interest in the topic? And that is grounding systems and lightning protection. Are you more design focused or operations focused? Helps understand who the audience is or what the perspective is. And here's how folks have weighed in on this. Looks like fairly prominent design interest. So the third question is, have you had a problem with surge or lightning? I'm really interested in the responses here because in the markets that we're intending to talk to, I think they're more prone to having these kind of problems, but we'll see. It looks like we've got most everybody in here. All right. Here's how the responses were for that question. And then finally, have you considered lightning protection as a design criteria? And with as much design focus, I expect this is going to be fairly heavily swayed in one direction or the other. All right. Here's how folks segregated themselves on this topic. Excellent. Today, I'm happy to introduce our guest speaker. Ivan Grobbelaar started his career working for the utility provider in South Africa and then moved his focus towards telecommunications when he worked for one of the largest telco companies in Africa. Today, Ivan is a registered professional engineer at the DEHN Africa facility. He's responsible for managing the engineering team providing technical support in lightning protection, surge protection, and earth termination system designs. Now, in the interest of trying to avoid technical problems for this presentation, we've pre-recorded his material so that he can join us online real time and answer questions as they come in. So both Ivan and his US colleague Stephen Weber will be available online. So by all means, submit your questions as we go through the presentation. And then we expect to have 10 or 15 minutes at the tail end to answer any remaining questions.
Hi, everyone. Thank you for joining this webinar today. The webinar is regarding designing grounding systems that not only safely dissipate fault currents, but also disperse lightning current effectively. And the idea around this is based on a lot of years of research and knowledge from DEHN. So DEHN is a 110-year-old lightning protection company, making us the oldest lightning protection company in the world. And this has given us access to the way we see lightning, a lot of research to change and so on. And the idea is for us to always pass this knowledge over the public so that you can understand lighting better and design and keep this as a design consideration as well. Okay, so my name is Ivan Grobbelaar. I'm the senior engineer at DEHN Africa in South Africa. The company does, however, have subsidiaries all over the world, so there is support in almost every country all over the world. So looking at an overview of what we want to touch on, the most important points is we first want to understand the difference between power frequency, which could be 60 hertz or 50 hertz, and how it's different when compared to lighting current. After that, we want to look into how we model for power frequency and how that changes when we start modeling for lighting frequency, and we do this using a very advanced software called XGSLab. During this, we will touch on the basics of safety analysis for human bodies, so step and touch voltage, which was discussed in a lot of previous EasyPower webinars. And then the illustration of the ground potential rise and power distribution and how it changes dramatically when injecting a fault current versus a lightning strike or injecting a lightning current. We will also then look at how lighting protection system components have their own test procedures and their test ratings and their own classifications, and how that's a little different compared to power system components and how they are tested, to ensure that these considerations are taken into account when we design systems to be safe for lighting purposes as well. And at the end, we will then illustrate a basic example using the XGSLab software and see how the results change for all of the points we discussed previously. So the first and most important point is power frequency versus lighting current. Now, one of the questions I usually get asked when people ask me, what do I do for a living? And I say that I'm an engineer that specializes in lighting protection and lighting current simulations. The first question is always, so what's your opinion on if we can harvest lightning, capture lightning and store and harvest lightning current and energy to be used later? So I want to invite you to keep this in mind as we discuss the differences between power frequency and lighting current, and to make this decision for yourself at the end, as you will see how everything is completely different to how we know power and current. So starting off first, lightning is not a sinusoidal wave. It's not constructed from a sinusoidal wave the way we know as 50 hertz or 60 hertz, alternating current, and so on. So lightning is characterized as an impulse. Okay, so it's a single impulse. And the way this impulse is characterized can also change depending on what sort of lightning strike you're looking at. So if we take a step back on what type of lightning strike, so it's actually true that you do get a lot of different ways that lightning makes its way from cloud to ground, or sometimes even from ground up to cloud of high structures and so on, which is also makes up 10% of lightning strikes. So the biggest one that can carry the most damage is known as a first positive stroke. That means the lightning impulse is positively charged, and this wave shape by IEC is characterized as a 10/350 or 10 by 350 microsecond wave shape. So this 10 by 350 wave shape is denoted by these parameters on the input. So the first value 10 is denoted, or actually describes T1, which is the rise times to its peak value. So for example, in the first positive stroke, if we talk about T1 being 10 microseconds, it means that the impulse will have a rise time up to its peak value in 10 microseconds. T2, or the second value, 350 microseconds, describes that the wave shape will decay to 50% of its peak value over 350 microseconds. Now, this function is also known as the Heidler function, or a double exponential function, as it rises exponentially and decays exponentially. Now, there is a white paper that describes this from the developers from XGSLab with a professor, and they actually did some calculation to show if we had to characterize an impulse as a sine wave, what it would typically look like. So they consider the rise time itself, and for a 350 microsecond or first positive lightning stroke, they said the equivalent sine wave would be a 25 kilohertz sine wave. So what we immediately take away from this is that lightning has a very high frequency behavior. Now, first positive strokes only make up about 10% of all lightning strikes across the world. 90% of the strikes are characterized as first negative, meaning they carry negative charge, and the wave shape is completely different. So the rise time is much steeper, and the decay time is also a bit quicker. So if they then characterize that as a sine wave, it would be 250 kilohertz. Now, for this presentation, I decided to use the first negative in our calculations. As I said, this makes up 90% of lightning strokes. The subsequent negative is used to characterize subsequent strokes that occur after the first stroke. So when lightning actually strikes from cloud to earth, it ionizes a path from cloud to ground, and subsequent strokes will then follow on that ionized path. And that's the phenomenon where you see lightning striking and you see subsequent flashes as it strikes, but the lightning bolt or the lightning stroke stands completely still while flashing. Now, if we dig a little bit deeper into the wave shapes and how we characterize it, I described that for first positive stroke, which carries the most damage or the most energy, we talk about a 10 by 350 wave shape. And that is known as a direct lightning strike. So that's something that terminates directly onto your building or your installation, and so on. Now, this is not something that happens frequently. This is something that can happen once every 5 years or 10 years, depending on the calculation or the risk analysis conducted for that structure, but it's not something that happens commonly or frequently every year. Lightning can actually also strike in the vicinity of 500 meters around your building, or even 2 kilometers away from your overhead lines or power lines, and that lightning strike that terminates onto ground level then causes a mutual inductance or an induced effect over the lines of the structure 500 to 2 kilometers, 500 meters to 2 kilometers away. That casted lightning current or surge current is then characterized by an 8 by 20 microsecond wave shape. Switching surges that come from the utility or switching of loads are also characterized by this 8 by 20 microsecond wave shape. Now, this is the damage that most people experience during thunderstorms. It's actually not direct strike. So direct strike carries a massive amount of energy, which means that you will have physical damage to your structure or fire and so on, whereas an induced or indirect strike actually just causes a surge in the electrical system, and that's the common tick and your television is broken and things like that. It's not actually a direct strike, it's more surge. Now, to overlay the two wave shapes and to actually show you the difference, you can see the red curve being the 10 by 350 microsecond and the green curve being the 8 by 20. So the red being the direct lightning strike and the green wave shape being a surge or an indirect lightning strike. Now, both of these strikes actually peak at 40 kiloamps. So that means that we don't characterize this as the main factor for calculating damage based on surge or lightning strikes. It's all dependent on the wave shape. So if we look at the rate curve, as explained previously, we will peak at 10 microseconds, and we will decay to 50% of its value, which is 20 Ka, in 350 microseconds. Now, a surge is obviously a little bit quicker, but it decays much faster as well. So it reaches half of its value in 20 microseconds. So if we want to then investigate or calculate the energy associated with these waveforms, we take the integral, or the area under the curve, and you can immediately see that the area under the red curve is much larger than the area under the green curve. And that's why these direct lightning strikes cause so much more damage, and then also carry so much more energy in compared to a surge. Now, all these aspects need to be taken into consideration when we model, or we're modeling for a first positive, a first negative. What's the peak value, and what's the shape of the impulse that we're injecting? Now, the next few slides will then explain how we model power frequency versus lightning impulse using XGSLab. Now, to just do a quick recap, take a step back, which was explained in previous EasyPower webinars as well. It's just the concept of step-in-touch voltage. Now, this is extremely important for determining safety in substation areas or lighting protection systems and so on. Now, the hazardous conditions associated with electric shock is based on step and touch voltage in installations like substations and big switching yards and things like that. So the basic concept is this: current flows when there is a voltage difference between 2 points. Now, if we look at this picture, which is from IEEE standard 18, if we inject a fault current at this point, it creates this gradient, this voltage gradient or ground potential rise on the soil surface and in the subsurface layers. Now, if a person was standing on this graph with 1 meter spacing between his feet, 1 foot would be on one point of the curve and the other foot would be on another point. This means that there's a voltage difference, and this voltage difference will cause current to flow through the human body, which causes electric shock. Now, that's known as step potential. The same is true if someone stands and touches an energized part, which is bonded to the electrical earth, and there's a fault, and this metallic part gets energized, and it also enters the ground. If a person stands on a specific point on that voltage curve and touches the metallic part, which is on a different potential, that will cause current to flow from the hand to the feet. And that can also cause ventricular fibrillation and electric shock. So if you look at our little stick man, this is referenced from an IEC standard, also for human step-in-touch limits. You see that the current will flow from the hand down to feet. And that also causes touch potential and electric shock. Now, there's a lot of different theories and calculations for what the human body resistance is. And IEEE standard 80 refers to 1,000 ohm. But in all the different standards, it's always around this mark in any case. So that's a good basis to actually see or to start the calculation. Now, the human body resistance and so on also changes depending on the weight of the human in IEEE standard 80. And the idea is to limit the body current as much as we can as it flows. Now, in this calculation, as I said, the body impedance stays at 1,000 ohm. We know what the current limit can be. So we have to ensure that the voltage stays low enough so that we don't achieve that current in conjunctions with that body resistance. Now, XGSLab calculates these step-in-touch voltage limits for you. And at the end of the calculation, this graph is given, which illustrates the step voltage limit for a human being, in this case, 50 kilogram person, with the blue line, and the touch potential limit on the red line. So the voltage is on the y-axis and The tripping time is on the x-axis. So the tripping time is the fault clearing time when the circuit breakers will clear the fault. You can see that the longer the tripping time becomes, the lower the limit becomes, as the shock duration will increase. And as the tripping time gets shorter and shorter, the voltage limit actually increases, and the human body can take a little bit more. Now, this is critical because lighting, we talk about the microsecond range. As you remember, the 10 by 315 microsecond range. So the graph will be moved up way further back here, and the voltage limit will actually be very high as compared to power frequency simulations. Now, in this specific case, just to keep in mind, we're talking about a step voltage limit of 841 volts. Now, this limit is important for the example that we're going to do in subsequent slides and sections. So the ground potential rise, as we mentioned earlier, is when a fault gets injected into the earthing system or ground level, and it actually creates this potential gradient, as you can see on the right here, around this grid. So this grid is a top view around the building, and you can see the ground potential rise. Now, this ground potential rise, as we said, causes stepping touch voltage hazards. And the ground potential rise is calculated by a basic or simplified manner, like Ohm's law, where the ground potential rise in volts is the fault current magnitude multiplied by the grid resistance. Now, the grid resistance is highlighted in red in this case because the grid resistance is dependent on a lot of different factors, like the shape of the earth grid, the swirl conditions in the swirl model, and so on, which we will discuss next as well. And the current that will then flow through the body when we stand on different points of this graph may not exceed the allowable limits. And in that case, it means that the voltage limit, which was 841 volts, may not be exceeded when we stand on 2 points of this graph. So meaning we cannot have a voltage difference of 841 between any of the two colors as we stand on the grid. The standard defines that step distance as 1 meter. Now, in this graph, we can actually see the ground potential rise on the top view, and the current that may flow through the body is dependent on these voltage differences. So this is the ground potential rise. It's not the actual step voltage. It's just the potential rise that you see on ground level. As I said, the whole danger and the hazard around this is around the ground potential rise. So to ensure that we keep the ground potential rise as low as possible, or the voltage that you would experience on ground level as low as possible, is by ensuring that the grounding resistance is as low as possible. Remember, the formula is Ohm's law. So the fault current is going to be the fault current from the electrical system. But we can adjust the grounding resistance as much as possible to ensure a low voltage or ground potential rise on ground surface level. We can also create an equipotential plane, an equipotential between metallic parts by means of bonding, meaning that we will ensure all the voltage would be the same across the area where people can walk as an equipotential plane, so that there's no differences for step potential, and also that there would be no differences when touching metallic parts with reference to the voltage experienced on ground level by means of bonding. Then one of the other methods is to use swirl covering material. So that's typical where you would see in substations washed granite or substation gravel that covers the surface layer of the entire substation. This is to ensure insulation between the human body and the actual ground potential rise. And it just adds to an insulation level on the grounding level. So as I mentioned, the grounding resistance is dependent on a lot of factors. You can change the grounding resistance by changing the grid shape, material, and the swirl resistivity. So you can also enhance the swirl conditions. This graph is also calculated using XGSLab software from a lot of field measurements. And in this case, for our calculation today, we constructed a two-layer swirl model, which has a swirl resistivity on the upper level of 1,000 ohm meter for 1.5 meters deep, and it then after that continues as 200 ohm meter down to the depths. In this case, we can see that the grid is safe against step potential. So in the previous graphs, I actually showed you the ground potential rise you would see on surface level. And then this graph just shows the actual step voltage. So it shows the difference in voltage between points on the graph. And you can see the highest voltage difference is 740 volts, meaning that we do not exceed the 841 volt limit that we calculated as the allowable or the safety limit in our case. And that's because we have an equipotential plane with the way this grounding grid is meshed quite heavily. Now, poorly designed grounding grids will not ensure that we have an equipotential plane, and that will start causing step voltages and touch voltages because we're not ensuring the same voltage throughout the system. If we have our same grid shown previously and we just remove some of the meshed conductors, you can start seeing on the results that you would start to see these voltage peaks, and there's not that beautiful equipotential plane of the same voltage all across as people walk. So if someone had to stand on these very red points and the more pink points, and they would experience a very high voltage difference that can actually cause current to flow through the body and electric shock. Now that's the challenge with lightning. Lightning creates an extremely high voltage gradient. And that's why a system that is designed to be safe for 50 or 60 hertz at power frequency might not be safe against lightning frequency. As you remember in the white paper I explained previously, we spoke about 25 kilohertz, 250 kilohertz, and it goes up and up. And lightning is known to have high frequency behavior, and it can change from DC up to 10 megahertz in seconds, microseconds even. And that creates a very high ground potentialized steepness. And the other problem is also that lightning does not come in at 1 kiloamps or 360 amps. In lightning terms, we talk from 3 kiloamps up to 200 kiloamps. We've done research studies where we've measured 370 kiloamps. And this very high fault current, if you will, combined with a high frequency, creates a very steep voltage gradient with a very high voltage value as well due to the very high current. Okay, and we do get asked this quite a lot. So lightning has lightning protection levels to which we design to for our electrical system and for the lightning protection system. And it changes from a lightning level 4, being the least amount of protection required, up to level 1. And this level is determined by means of a lightning risk analysis in accordance with IEC 62305.2. And this takes a lot of factors into consideration, like the lightning activity in your area, the dimensions of your building, fire risk, and so on. But it's worth knowing what lightning level you should design to. Now, if we took the same situation we had previously of our grounding grid that was poorly designed, in that case, I injected 360 amps of fault current into the grid. If we use the same fault current of 360 amps, but I just change the frequency to a representing frequency of 250 kilohertz for first negative, we can see already that the equipotential plane is completely gone, purely based on the frequency and not even the actual fault current. So what's also important to keep in mind is using this XGSA frequency domain module, we give representations of lightning based on those frequencies that were estimated for an impulse. These are just representations to give nice visual aspects and nice visualization of what to experience from ground potential rise. There's a different XGSA module called the XGSA TD, or the time domain module, which we use to actually characterize lightning impulses. But in a lot of the slides, you will see that I use the frequency domain module just to give nice overview and pictures to actually graphically interpret what you see. So on this graph, you can obviously see there's a very high steepness, purely based on the frequency. And this is a top view where you can see also that the Q potential is completely gone. What's also important to note is, in this case, we do exceed then the step voltage limit. So this is a step voltage graph, and we are far off our 841 volt limit for power frequency, for example, but not necessarily for lightning frequency as we move up the graph and in a shorter time, fault clearing time. Now, to further investigate the lightning protection capabilities or the performance of such a grounding system, we need to also understand that components are tested differently for lightning frequency and lightning currents, because these are very high currents with very high mechanical strain. And there's a lot of different parts that we do test. We test anything from clamps to spar gaps to isolated lightning protection systems. And what's quite interesting is at DEHN, you can actually see this is our lighting generators. So at DEHN, we have a facility in Germany where we can test up to 400 kA 10 by 350 or direct lightning currents. And we can test all the components and surge resistors and do a lot of research and development. To the best of my knowledge, last I heard, this is the biggest lightning current generator in the world, actually. So it's actually, there's a lot you can do with this around testing up such high currents. So during the lightning protection or the lightning component testing, there's a lot of different tests involved that I will explain in more depth as well. So it's anything from force tests or torsion tests, and then tests against the atmosphere, salty air, sulfurous atmospheres, and things like that, and actual mechanical testing and electrical testing. What's important to note on this slide is that the testing standard that we use is known as the IEC 62561 series. It's been adopted by a lot of different countries all over the world, but the concept stays the same in most cases. Now, IEC 62561 is actually broken up into 8 parts. And for the purposes of this webinar, we will look at part 1, which is connection components, or the clamp, which you saw in this case. So if we then look at the testing requirements for a connection component, you see that, as I mentioned, we actually have to then test for the salt mist treatment. So it's a salt air atmosphere around the coastal regions and so on, to ensure that it doesn't corrode heavily and loses its integrity and the dimensions and the cross sections of the clamp itself. There's also a sulfurous atmosphere test. So for the oil and gas industry, where we might have corrosive atmospheres and corrosive areas, we can actually corrode certain materials and clamps much faster, much more accelerated. And they do a mechanical force strength test. And at the end of all these tests, when the clamp is heavily corroded from saltness, sulfurous atmospheres, and pulled around a bit for force test, it still gets injected with lightning current to ensure that the clamp itself will safely conduct the lightning current through the components that it's actually connecting, and then it will receive a pass. This is an example of a manufacturer's test report, and this is typically what you would look for. So you can see for first positive stroke, we explained in the beginning, 10 by 350 microsecond, it will either be tested according to a class H or class N, meaning that this clamp will be able to handle either 50 kA, kiloamps, or 100 kiloamps. And in this specific test report, they talk about the clamp, for example, connecting an aluminium 8mm conductor on both sides, and then it will do 100 kiloamps. If we had to connect a 10mm diameter galvanized steel conductor to an 8mm reinforcement conductor, it will only be able to carry 50. So these are things that you have to take into account when you do the lighting simulations using software. So in XGSLab, we can actually see the current distribution through the system when we do these lightning injections, and actually make sure that the components would not be overstressed, and that there's not excessive lightning currents flowing in parts of the system that might have smaller clamps or weaker clamps, for example. Now, in this last portion of the webinar, I would like to then show you an example of designing a grounding system and how we would then adjust that poorly designed grounding system to also safely carry lightning current and disperse lightning current as well. As mentioned previously, so lightning is an impulse. It's characterized by an impulse wave shape, not a sinusoidal wave shape. And we do use sinusoidal wave shapes to represent some ground potential graphs and so on, but in essence, lightning would be an impulse. Now, as I also mentioned in the beginning, 90% of lightning strikes may be considered to be first negative impulse. And that's from IEC 62305, which is the main lightning protection standard across the world. And in Annexure B of Part 1 of the standard, they then give you the wave shapes you should use when doing simulations. Now, you can see that for simulations, we never see, or we don't see any 10 by 350 microsecond or 8 by 20 microsecond wave shapes like we discussed. To test wave shapes, that's because we use adjustment factors and so on when doing the simulation. So we would have had a 10 by 350 microsecond wave shape. In this case, for first positive, it would be 19 by 485 microsecond. But for first negative impulse, which we'll use now, we will be using 1,82 by 285 for this webinar, for this example. Because lightning protection level 3 and 4 is the most common all over the world, we will then use 50 Ka in the first negative impulse. That will cover most of the situations that you'll see all over the world. So then if we enter these values into the XGSA time domain or XGSA TD module of the software, they actually give you a lot of flexibility to adjust the wave shape exactly the way you want to. And you then enter the values same way it's read off from the standard. So it's an adjustment factor, K factor, and then the rise time and the fall time, just T1 and T2, 1,82 by 285. The 50 Ka is injected in the same manner you would have injected a fault current within the system. Now, if we look at that same grid that we want to adjust, as I said, we're going to inject 50 Ka of first negative lightning stroke, lightning current. The grounding resistance we calculated previously for this was around 10 ohms, which is also sort of the benchmark or the target we try to hit when we design for lightning protection systems. The swirl model was calculated to be a two-layer model, as shown previously as well. And in this case, no swirl covering layer has been added yet. So no substation gravel or any insulating material has been added yet. Now, the steepness that we described earlier due to lightning current is not such a big hazard necessarily within the building, but around the building outside where people would walk, especially walkways and things like that. So we also need to address the very high peak current around, or the peak steepness of the ground potential rise around the building as well. And when people actually touch parts of the lighting protection system, it will be connected to the grounding system and also the step voltage. People would walk around the building based on a 1 meter spacing between their feet. So if we just want to start the investigation to see what we are working with, we inject on the same earthing grid at high frequency, we inject the 50 kiloamps. And you can immediately see the step voltage is calculated to be around 650 kilovolts for 50 Ka first negative stroke. And in this case, it's also calculated or estimated with a 250 kilohertz sinusoid. Now, the 650 kilovolts is far above what is considered to be safe for lightning step limits or allowable limits. There are a lot of different theories and calculations and models around what's seen as the allowable step touch voltage limit when we speak about light. So in the beginning of this webinar, we spoke about the calculation for 70 kilogram and a 50 kilogram person using IEEE standard 80. That's for power frequency. As I mentioned, when we make the tripping time or the fault clearing time of circuit breakers faster and faster, the limit actually increases. Now, based on a lot of different sources and models, this is what some people over the world have come up with. So there's an IEC standard that we do reference a lot through this webinar as well. It talks about 25 kilovolts, and then other different body models. So for the purpose of this webinar, we will work on the 25 kilovolt limit, as this is one of the most common ones that I've come across in industry. And we then have to control to ensure that there's no step potentials exceeding 25 kilovolts on the gradient. Now for touch voltage, it's also a little bit different. So for touch voltage, when lightning passes through a conductor, again, it will pass through the human body into earth where the voltage is different. But if we merely then also just insulate a down conductor, normal insulation, like PVC pipes or things like that, also will not suffice. So the standard says that this insulation must be able to withstand 100 kilovolts of flash over voltage. The reason is that you create an inductive loop between yourself and the ground, and you are a conductive component, and lightning will actually then flash through the insulation due to this mutual inductance loop. Now, the ways to mitigate touch voltage is directly described in IEC 62305 Part 3, which is the lighting protection standard. What it says in that part is that you can ensure that swirl covering material is applied with a 3-meter radius around the down conductors, and that a 3-meter radius of clearance is kept around down conductors. Install warning signs so people do not touch down conductors during lightning storms. The standard also says that those touch voltage hazards may be ignored if the building has more than 10 down conductors, because the lightning current dispersion through more than 10 down conductors would be so much that each down conductor would not carry sufficient current to actually cause touch voltages. If this is not possible, you're not able to achieve this, you can make use of touch-safe insulated down conductors. And as I mentioned, it should have 100 kilovolts insulation for a 1,2 by 50 microsecond voltage wave shape. So that's also dependent on the rise time to not overstress the cable. It's not 100 kilovolts at power frequency, but rather 100 kilovolts at 1,2 by 50 microseconds. So this is an example of a special lightning insulated down conductor that can be used to ensure that our installation will be safe against touch voltages, ticking the first box of our lightning protection system and making sure that it's safe against lightning currents. The second issue that we need to address is to reduce the ground potential rise and thus reduce the step voltage hazards. We're going to do this again by using the XGSLab software. As I mentioned previously, we can firstly apply a swirl covering layer, also known as SCL, between the human body and the ground potential rise, meaning that we will then increase the resistance between the two significantly to ensure that there's not a high voltage above that resistance so that can cause hazardous step voltages or current to flow through the body. One of the most common ones that we typically use is the washed granite, similar to 3/4 inch gravel, and that has a swirl resistivity of 2 mega ohm meter when it's dry and 10 kilo ohm meter when it's wet. Now we typically use the wet conditions because when there's lightning it rains, and we would have wet conditions as well. So for the purposes of this example, we will then work on a 10,000 ohm meter, and that's the first thing we apply. We apply a 10,000 ohm meter and we work on a 150 millimeter thickness application, that's the first mitigation factor we use against step voltages. The second thing we can do is we can adjust the shape of the grid. So this is an example on the right of potential control in the ground at walkways or around structures. For example, this was a floodlight or a mobile telecoms mast or something like that. If you look on the left, we see that at different depths we keep installing conductors further and further away. And by doing this, we actually control that steepness factor of the ground potential rise to ensure that we don't have significant differences between points if someone had to walk on. So we can actually then apply this method as well. If we then look at our modified grid, this is what it looks like. So we have the meshes firstly put back to ensure we get an equipotential plane as much as possible. And then we apply the rings at different depths, as you can see. So this at the bottom is the side view of the grid from this way, and this is the side view from this way. So you can see that we apply these rings around the grid at different depths. And we start controlling that ground potential rise curve and the steepness of the curve from the top all the way down to a safe distance away from the building as well. Now, if we inject the same 50 Ka into our new grid for very high frequency, you can see that we've suddenly established then our equipotential plane. So there's not a lot of big differences in voltages on this graph that can cause step voltages. If we look at it then from the top, we can see that this is a graph now of the step voltages and of the ground potential rise itself. You can see that we do not exceed the 25 kilovolt limit that we were aiming towards. And the system is then also safe against step voltages. Now, I mentioned briefly that we use the high frequency components, in this case 250 kilohertz, to give graphical interpretation and graphical images and a nice views of how we describe ground potential rise. But the correct manner is to use an impulse, which we describe to be a 1,8 by 285 microsecond impulse. To do that, the software then breaks that impulse up into a set of frequencies. In this case, I chose 167 different frequencies. And we do this with the XGSLab TD, or the time domain module. And the software will then calculate along this line, on each point on the line, 167 times what the voltage is all along this line, because we chose 167 frequencies inside that impulse. Now, if you look at this line, this is the origin of the line, and as it passes through the length of the line, I think in this case was around 12 meters, something like that. So you can see it starts at -3, and then there's the length, actually it's 19, sorry. And we then calculate the ground potential rise along this line on the graph as well. And this is what it looks like. So this is the result. The green graph shows the ground potential rise along that line. So the line is here on the x-axis, the 19-meter line, as you can see. And so the green shows the ground potential rise, and the red shows what the touch voltage would have been if there were conductive components. And then our limit, our 25 kilovolt limit, is on this sort of purple maroon line. And the step voltage is in blue. So you can see that our step voltage is far below what we consider to be the safety limit. So the grid is then safe against step and touch by making use of the insulated down conductors and this potential control in the ground. Lastly, we want to check that we do not exceed the currents that pass through this grounding system, and that's very easy. So we want to check the current distribution to ensure that our components are not overstressed. So if you remember from the test report, we spoke about 50 kiloamps, so we were not supposed to exceed 50 kiloamps. And to illustrate the difference between using a frequency version or the frequency module for estimation versus the actual time domain calculation, you can see on this case, we want to focus on the conductor that carries the most current, which is said to be 8.8 Ka. And if we do that same time domain calculation on that conductor, we see it's a little over 10 Ka. So that's the difference. But the main point is that in both cases, we didn't come near the 50 Ka tested value of the component. So we know that none of our clamps that we use to connect the grid will be overstressed. Okay, so just to take a step back and just conclude and just recap on everything that we spoke of. Due to the high frequency behavior and the high current values, fault current, impulse current values that lightning creates, it creates extremely steep and large ground potential rise plots. Now, to reduce the touch potential hazards around a building to fight against this ground potential rise, we use tested insulated down conductors or keep a 3-meter clearance distance around the down conductors. Put up signage to say that people should not touch the down conductors. And then the touch potential might be neglected if more than 10 down conductors are installed on the lightning protection system. To reduce the step potential, we want to establish potential control in the ground. So we want to establish equipotential plane and then steer and control the ground potential rise as it decays further away from the building. And we can use swirl covering layers to insulate the feet from the ground potential rise that you would experience during a lightning entering the grounding system. And then finally ensure that all your components are not overstressed in accordance with their tested capabilities by monitoring the current distribution to the earthing grid and so on. So that is the webinar. Obviously, if you have any questions, then you just ask them. Thank you. Thank you for your attention.
Great. So thank you to everyone that joined. First of all, I appreciate it. It was a very big turnout, a lot of attendees. So thank you very much from EasyPower and from DEHN. I actually received a lot of questions. Most of them are responded, or I think actually all of them are responded privately, but I think it would be good to maybe discuss some of them. And there was some relevant questions to most people as well. So the biggest question I got was from a lot of people actually is, to what point can we apply this design? So to what fault current can we apply this design? So firstly, it depends on a lot of factors. So the grounding grid in this case was designed based on the soil conditions, based on the fault current, based on the shape, the area we needed to cover as well. So it depends. You're going to have to actually do a design every single time. So it's not a standard thing you can just roll out. I mean, that's very important. The second big question I got was, can we just assume to always use first negative as the lightning strike or design according to first negative? That's, like we said, that makes up 90% of lightning strikes. So that'll cover 90% of situations. If you want to design according to worst case, you would need to design according to first positive. But in general cases, we design to first negative. We also got questions regarding the duration or the fault clearing time. So as I mentioned, fault clearing in lightning terms is in microseconds. So it's beyond what breakers actually do. So we design in the microsecond range. I think that's most of the popular ones, to the best of my knowledge. That it will also be uploaded, the recording, so you'll get to see that as well. We will also share some of the information of the presentation itself. What's also important to note, so we got questions about frequency, what frequency to use and so on. As I said, lightning changes frequency in that time span when we design. So lightning can range from DC to 10 megahertz in a couple of different points or values. So the values that you saw of 25 kilohertz or 250 kilohertz are just representative values to give you ground potential rise to the best of the best way we can fit the curve to an impulse. But you have to use the time domain module. You want to be very accurate as well. We also have some questions that ask, is the use of typical MV cables like XRP cables for down conductors acceptable? Yes. So the challenge is just that the XRP cable, as I mentioned, must be tested to a voltage wave shape of 1,2 by 50 microseconds, 100 kilovolts, and then you can use typical XRP cable for touch potential purposes. So that's directly referenced from the lightning protection standards. I think that covers most of it. We also have one more question. So what about step and touch limits for livestock and normal power frequency faults? So livestock is a bit different. Actually, I can find out, but I don't know what the body limit would be for livestock. But the challenge with livestock is obviously that their feet are further apart than human beings. So it means that they're more susceptible to voltage differences. They take up a bigger area on the voltage gradient curve. And another challenge opposed or in conjunction with this is that lightning current flows from the front legs to the hind legs or the other way around, which means it passes much closer to the heart to cause ventricular fibrillation. So it's much worse in livestock than compared to human being, but I'm not 100% sure what the actual limit would be. So to one more question. So we always design bare down conductor for buildings. Is that not recommended? So bare down conductor is fine. As I mentioned in the standard as well, it's the most common practice. To mitigate the touch factor, you just need to keep a 3-meter clearance around the down conductor during lightning protection. And you have to use substation gravel or insulating material around down conductors. You can also install signs to say that you should not touch the down conductor during lightning storms. Or, as I mentioned in the webinar as well, if you have more than 10 down conductors in your lightning protection system, the touch voltage can be neglected from the lightning protection standard, which is IEC 62305. So it looks like most of the questions were covered. So if there's any other questions, you can obviously forward to us as well. Thank you. Thank you so much.